Moving a coil out of a magnetic field. A square loop of wire, 0.40 meters on each side, has a resistance of 0.14 ohms. The loop is moved at a constant speed in 0.20 seconds from position 1, where a magnetic field is 1.3 Tesla, to position 2, where the magnitude of the magnetic field is 0. A. What is the induced EMF in the loop during this period of time? B. What is the direction of the induced current in the loop? C. What is the magnitude of the induced current? D. What is the power dissipated in the loop? And E. How much force is required to move the coil from position 1 to position 2? What is the induced EMF in the loop during this period of time? Well, perhaps you remember this equation, the motional EMF. So what is that telling us we need? We need the velocity. So how do we find the velocity or speed of the coil? Well, let's see. The coil travels a distance of 0.4 meters before leaving the field. So velocity is distance over time. So we have 0.40 meters divided by 0.20 seconds, and we get a velocity of 2 meters per second. So you can never forget mechanics. Now we just substitute in our givens and our newfound velocity into the BLV equation, and we get an EMF of 1.04 volts. What is the direction of the induced current in the loop? Well, as the loop leaves the magnetic field, the magnetic field decreases. So the induced field in red will be in the same direction, which is out of the page, opposing the change in the original field, which is this black field, right? So it doesn't want to lose the magnetic field, so it generates a magnetic field in the same direction, which is out of the page. Now apply the right-hand grip rule, where you're going to grab the right side here, and you want your fingers here out of the page. So it's hard, I can't really draw this too well, but picture these fingers coming out of the page in the same direction as a magnetic field. Using your right hand, your thumb should be in this direction, which shows that the current, the induced current, is going counterclockwise. What is the magnitude of the induced current in the loop? Good old Ohm's law here. We put our induced EMF for voltage, 1.04 volts, over the resistance in the loop, 0.14 ohms, and we get a current of 7.4 amps. We want the power dissipated in the loop, so we use our power equation, P is equal to IV, or P is equal to current times EMF, substitute in our values that we found and were given, and we get 7.7 watts. How much force is required to move the coil from position 1 to position 2? The external force will be equal and opposite to the magnetic force that is acting to keep the loop in the field. And that's our Philb equation. Current times length of the wire times the magnetic field. So you substitute in your givens. Here's the current, here's the length, and we're talking about this length right here, but since it's a square, it's the same for each side. But again, we want to talk about this length. And there's the magnetic field, and we get a force of 3.9 newtons.